Welcome to the talk for STOC 2022, the exact complexity of pseudorandom functions and the black box natural proof barrier for bootstrapping results in computational complexity. I'm Jiatu Li from Tsinghua University, and this is a joint work with Zhiyuan and Tianqi. In this talk, I mainly want to discuss the two main motivations of this work, as indicated in the title of the paper. The first motivation is to understand the complexity of cryptography, which means we want to know how much computational resource we actually need to build crypto systems. We want to construct efficient pseudorandom functions as well as other cryptographic primitives in various circuit classes and prove their optimality by showing matching circuit lower bounds. The second motivation is to understand the limitation of current circuit lower bound techniques using the constructed pseudorandom functions. This is not a surprise because the famous natural proof barrier has established a connection between circuit lower bound techniques and pseudorandom function distinguishers. We actually get a fine-grained version of the barrier and show that some new techniques, which is possibly not natural, is also not capable to prove strong circuit lower bound. Here is an overview of today's talk. We will first outline our results in pseudorandom functions, give some intuition how it is proved, and then discuss why it indicates that some circuit lower bound techniques is not capable to prove strong results. Finally, we will give an interesting open question. Now we first review some basic definitions. A pseudorandom function is a function that looks random. The syntax of it is an efficiently samplable distribution Dn of n-input single-output Boolean functions. And the security condition, which asserts that it looks random, is that a random function drawn from this distribution is indistinguishable from a truly random function if the adversary is probabilistic polynomial time and has only arc accesses to these two functions. Pseudorandom functions has a central role in private key cryptography. It is known that the existence of pseudorandom function is equivalent to the existence of pseudorandom generators and even one-way functions. With such a simple and expressive object in hand, we can easily construct most of the central primitives in private key cryptography, like symmetric key encryption, message authentication code, and key derivation. Some variants of the pseudorandom functions is also helpful to construct advanced crypto systems, like fully homomorphic encryptions and indistinguishability authentication. Before actually consider the complexity of pseudorandom functions, we need first to clarify the definition of complexity. There are two phases in the application of pseudorandom functions. The first phase is sampling, which means we want to draw a particular function or the description of function from the distribution of functions. And after we do that, we need to support the evaluation of this particular function drawn from the distribution on a point queried by the adversary. Both of these two procedures involve computational overhead, but the second procedure is more important, so similar to previous literatures, we mainly consider the circuit complexity of the evaluation phase. Here is the formal definition. Let C be a circuit class, and the circuit complexity of a pseudorandom function Dn is defined as the maximum C circuit complexity of the functions on the support of Dn, which means after we draw the function from the distribution, how much computational resource we need to evaluate it. The circuit classes we mainly consider are B2 circuits, AC0 parity circuits, and TC0 circuits. B2 circuits are unrestricted circuits with fan-in-2 gates computing arbitrary binary Boolean functions, and it is also known as a general circuit. AC0 parity circuits are constant depth circuits with only AND, OR, and parity gates of unbounded fan-in, and it can also consist of NOT gates of fan-in1. Here parity refers to the XOR of all its input wires. TC0 circuits are constant depth circuits with linear threshold gates. On each of the linear threshold gates, we have the weights W and threshold beta, and it output 1 if and only if the weighted sum of the input bits is above the threshold, and it can be considered as a half hyperplane on the Boolean hypercube. The complexity of pseudorandom functions in these circuit classes has been studied in previous works. By the seminal work of Ishai, Kushilevas, Ostrovsky, and Sahai, Pseudorandom functions are computable in linear-sized B2 circuits assuming one-way functions exist. It is well known that pseudorandom functions are computable in polynomial-sized AC0 parity circuits and TC0 circuits under standard assumptions. There are also plausible pseudorandom function candidates computable in n to the 1 plus epsilon size TC0 circuits based on heuristics. On the negative side, by the connection between circuit lower bounds and pseudorandom functions, there is no PRFs computable in polynomial-sized AC0 parity circuits secure against all quasi-polynomial time adversaries. In this work, we proved tight upper and lower bounds for the complexity of pseudorandom functions in B2 circuits, AC0 parity circuits, and TC0 circuits. Assuming the existence of polynomial-sized pseudorandom functions in corresponding circuit classes, we can construct PRFs in B2 circuits of size 2n plus little o n, AC0 parity circuits with little o n gates and 2n plus little o n wires, and TC0 circuits with steps d and n to the 1 plus 1.61 to the minus d wires for large d. On the other hand, we also show that all these upper bounds are near optimal. To compute pseudorandom functions, it requires B2 circuits of 2n minus 2 gates, AC0 parity circuits with 2n plus omega square root of n wires, or TC0 circuits with steps d and wire complexity n to the 1 plus c to the minus d for some large constant c. Note that all our lower bounds hold unconditionally and all our upper bounds hold under the weakest possible assumption, namely the mere existence of pseudorandom functions in these circuit classes. This figure helps to explain why we think our exact complexity result for PRFs can be interesting. Imagine the arrow in the middle as circuits ordered by their size. When we are considering small-size circuits, like B2 circuits of 2n size, AC0 parity circuits of 2n wires, and depth d TC0 circuits of slightly superlinear wires, there is no PRF, which means every distribution is unconditionally detectable from truly random. Like the cat, it can be distinguished from a truly random noise by only arc accesses. And when the circuit size becomes slightly larger, like B2 circuits of 2n plus little o n size, then PRFs exist under standard assumptions, which means there is a hard distribution of circuits that looks random. It seems quite mysterious that the mystery of pseudo-randomness hides behind the small gap between our upper bounds and lower bounds. Now we move on to discuss the intuition behind our results. Let's first look at the circuit upper bounds for pseudorandom functions, and we mainly focus on the 2n plus little o n upper bound for B2 circuits. The main technical tool for our pseudorandom function upper bound is a trick discovered by Levin. It says that if f is a pseudorandom function and h is a universal hash function with polynomial output length, then the composition of f and h, where the output of the hash function feeds the input of the pseudorandom function, is also a pseudorandom function. This is called a domain extension trick since we can construct a pseudorandom function with larger input length using a pseudorandom function with smaller input length. It has also been discovered that this method can be used to reduce the complexity of pseudorandom functions. Suppose that we have an inefficient PRF, say it can be computable by n to the 10 size circuit, and we want to improve the efficiency of it. Since we can hide it behind a universal hash function, as long as we choose the output length of the universal hash function to be smaller than n to the 0.1, the complexity of the original pseudorandom functions will be at most little o n, which means that the complexity of the new pseudorandom function mainly depends on the complexity of the hash function. Therefore, the problem of constructing efficient PRF reduces to the problem of constructing efficient hash functions, and actually IKOS proved the linear upper bound by unconditionally constructing linear-sized computable hash functions. But here is a problem for us. Typical constructions of hash functions involve low complexity error-correcting code, but it is hard to optimize the constant behind the big O notation, so we had to find some other constructions of hash functions. The first observation that leads to our constructions of pseudorandom function is that we do not need the full power of universal hash functions. Actually, we only need it to be almost universal, which means that the collision probability of the hash function is negligible in n instead of exactly 2 to the minus m for output length m. Then we observe that to construct these almost universal hash functions instead of universal hash functions, we also do not need the full power of error-correcting codes. We can actually take out an intermediate primitive called one detector or range detector to construct our almost universal hash functions, which is much easier. To complete our construction, we need to observe that one detectors are actually computable by two n-size circuits, and this is proved by a simple but tricky argument using the existence of explicit undirected graphs with large girths. Now we move on to discuss intuition behind our PRF lower bounds. To do that, we need to borrow some ideas from explicit circuit lower bound techniques. A typical circuit lower bound proof involves two technical components. We need a lemma for the circuits, which shows that all small-size circuits have certain properties. And we also need a compatible hard function that do not have the property. Therefore, this function cannot be computable by small-size circuits. In our case, the hard function is chosen to be a pseudorandom function, and we need to show that there is no distribution over small-size circuits computing a PRF, or equivalently, every distribution over small-size circuits can be distinguished from truly random functions by only oracle accesses. The key observation leading to our PRF lower bounds is that the lemma for the circuits in some of the known circuit lower bound techniques can actually imply a black box procedure that recognizes small-size circuits, which means to distinguish them from truly random functions. Therefore, we can adapt these black box lower bound techniques to prove our PRF lower bound. To give a concrete example of our technique, we can take a closer look at our slightly superlinear lower bounds for pseudorandom functions against TC0 circuits. Our plan is to apply the technique of Chen, Sasnam, and Srinivasan on average case lower bounds and set algorithms for TC0 circuits. The first step is to analyze their main lemma for the circuit, which says that for all slightly superlinear sized TC0 circuits, if we apply firstly a random restriction to some of the input variables and another smartly chosen restriction depending on the circuit, then with nice probability, a whole layer of the gates in this TC0 circuit will be trivialized. They prove their lower bounds by applying this restriction procedure until the TC0 circuit simplifies to a single threshold function, whereas the parity function will not be simplified in such manner. However, their strategy cannot be directly used to prove PRF lower bounds. Although the behavior under iterated restriction indeed gives us a difference between small-sized TC0 circuits and random functions, it cannot be used to prove PRFs, since we cannot implement the white box restriction with only oracle accesses to the function. Therefore, the second step of our proof is to extract a black box property from this white box restriction lemma. We prove by induction that small-size multi-output TC0 circuits are not sensitive. That is, if we flip a random bit of a random input with nice probability, the output will remain unchanged. On the other hand, the output of a random function will change with high probability while flipping any bit of its input. So we obtain a property that distinguishes small-size multi-output TC0 circuits from truly random functions that can be tested with only two oracle accesses. Finally, we can obtain a PRF distinguisher for single-output TC0 circuits by standard transformation of single-output to multi-output pseudorandom functions. This leads to our final PRF lower bounds. It is worth noting that our techniques to prove complexity bounds for PRFs can, at the same time, resolve the exact complexity of almost universal hash functions. Recall that our upper bounds are proved by constructing efficient almost universal hash functions. And from the lower bounds of PRFs, we can also derive conditional lower bounds for almost universal hash functions. By Levin's trick of domain extension, if we have efficient hash functions and polynomial-sized PRFs, we can actually construct efficient PRFs. Reading this in contrapositive, we know that assuming the existence of PRFs, PRF lower bounds immediately imply hash function lower bounds. By taking a closer look at our proofs, we can also make the lower bounds unconditional, leading to exact complexity results for almost universal hash functions. In the third part of the talk, we will discuss how we can interpret our result as the barrier for the bootstrapping results in complexity theory. Proving strong explicit lower bounds is the holy grail of complexity theory. Despite of decades of efforts and impressive progress in restricted circuit classes, we still know little about strong circuit classes like general circuits or formulas. For general circuits, we cannot even construct any language in NP that requires 6n size circuits, although it is widely believed that NP requires super polynomial size circuits to compute. For formulas, we cannot prove a super cubic lower bound for NP, while it is believed that P requires super polynomial formular complexity. There are huge gaps between what we believe and what we can prove, and it is explained by formal barriers such as natural proof barrier that applies to most of the known circuit lower bound techniques. Bootstrapping results present a new approach to bridge the gap between what we want to prove and what we can prove. A bootstrapping result, which may be formulated in different settings such as harness magnification or quantified randomization, shows that a mild improvement to some known results in circuit complexity can lead to huge breakthroughs. Here is an example of bootstrapping result in the context of harness magnification. Chen Jing and Williams proved a quadratic lower bounds against probabilistic formulas for certain problems in NP, and they show that if the lower bound can be improved to truly superquadratic for the same problem, it will imply breakthroughs, such as fixed polynomial size lower bounds for NP. The bootstrapping results revealed an indirected way to resolve the open problems in circuit complexity, and most interestingly, it would bypass known barriers such as natural proof barriers. Although most of the researchers agree that bootstrapping results present a new interesting connection between weak and strong results in circuit complexity, there is a lack of consensus in the interpretation of them. From an optimistic point of view, it gives a new approach to resolve major open problems. From a pessimistic point of view, however, it shows that even slightly non-trivial circuit lower bounds can be extremely hard to prove. In order to understand the actual strength of the bootstrapping results, we should set a barrier to address the weakness of current techniques for bootstrapping results. In this paper, we introduce a new barrier called black box natural proof barrier for two natural classes of techniques of bootstrapping results. Intuitively, we show that bootstrapping results that essentially use the power of arithmetic codes and hash functions cannot be combined with black box circuit analysis techniques to obtain a breakthrough. Let's use the harness magnification results of Chen Jing and Williams to explain the ideas of our barrier. This figure shows the bootstrapping frontiers in their works. We can prove near quadratic lower bounds against probabilistic circuits, while improving it to truly superquadratic lower bounds would imply breakthroughs. From the techniques used to prove near quadratic lower bounds, we can actually derive a matching circuit lower bounds for PRFs. The techniques for the bootstrapping side, on the other hand, requires efficient constructions of hash functions, which will lead to a PRF upper bound. Improving their results on both sides will, at the same time, improve the upper and lower bounds for PRFs. This means that if we stick to their techniques on both sides, it is unavoidable to refute the existence of PRFs in order to bridge the gap between the bootstrapping step and the provable lower bounds. This barrier actually applies to most of the interesting bootstrapping results, and we refer interested listeners to our paper for more examples and detailed discussion about our new barrier. In the final part, we want to discuss an interesting open problem. From the very beginning of the talk, we have mentioned the two main motivations of this work, that is, to understand the complexity of cryptographic primitives and to give insights about circuit complexity using cryptographic constructions. As we have established the result for PRFs, the most interesting open problem is, therefore, to obtain similar results for other cryptographic primitives. Concretely, we want to know whether we can show tight complexity bounds for other crypto primitives, and whether we can use reasonable constructions of it to address the limitation of certain kinds of circuit lower bounds techniques. For instance, can we prove similar results for collision-resistant hash functions, or even certain formalization of random oracle hash functions? This is the end of the talk, and thanks everyone for listening.